one of the things that we're going to focus on right now is what is the relationship between rate of reaction and concentration, because this is going to have a lot of impact on various things. So I'm going to show you this graph here. And it's a plot over time, because again, we said that rate has to have some sort of time component of monitoring this reaction. So a plot of concentration as a function of time, monitoring this reaction. You can see in this reaction that it's 2 moles of nitrogen monoxide reacting with oxygen gas to form 2 moles of nitrogen dioxide gas. In the chem activity 11, we actually introduce this reaction in the context of environmental chemistry. So when you take a look at that, you'll see this reaction. What we're interested in knowing, though, is one, what the rate of reaction is, and secondly, how changing the concentration of one of the reactants can impact the rate. You'll see that in this case, we're actually, for whatever reason, able to monitor the oxygen concentration over time. That's often actually really difficult to pick a particular reactant and be able to have some instrument that can actually measure it. So the way that we monitor the rate of reaction often is related to what can you measure? What can you actually see? What can you determine, let's say, with a pH meter or a conductivity meter or a gas pressure sensor? But for whatever reason, let's say we can monitor the oxygen gas. That said, you could also determine the rate of reaction by looking at the disappearance of nitrogen monoxide or the appearance of the nitrogen dioxide. So it's whatever you can monitor. Now you can see that I'm monitoring the rate of the reaction over time. But what I'm going to ask us to focus on is what is referred to as the instantaneous rate at time equal to 0. Another way of saying this instantaneous rate, is actually the initial rate. Now, again, in Chem Activity 11, this will be broken down a little bit more carefully, but you can kind of think of it as the initial rate will be the change in concentration of our oxygen gas over the change in time. But the idea is that we're in a sense kind of applying calculus principles here, such that we make our change in time shorter and shorter and shorter until essentially we're looking at a minuscule change in time at the very beginning of the experiment. Now we say time equal to 0, but it's not quite time equal to 0, because if it was really 0, there'd be no reaction, right? The reaction hasn't started. So it's like the reaction starts and then stop. And what's the rate right at that point? And it's an instantaneous rate because it's right at that point. It's not an average rate throughout the whole experiment. It's just right at that point where I'm showing you with the arrow here. So you can apply calculus principles, or maybe even more simply, if you had these sorts of plots right at the 0 point, you could draw a line to the tangent and find the slope. So we're looking at the change in y over the change in x. Essentially, it's the slope at each of these points. Now you can see that what I'm doing here is I'm looking at the instantaneous rate under 2 different conditions. I'm looking at, well, what's the rate of disappearance of oxygen gas when the initial concentration is right here, which would be 0.005, and then whatever the number of significant figures. And you can see that there's an answer to this. If we take the slope corresponding to that initial concentration, we get this number, 1.0 times 10 to the minus 6 molar per second. Look at those units, molar second to the minus 1. Another way of writing that is molar per second. And as you might expect, change in concentration over the change in time. It's a rate. If we bump up the initial concentration to 0.01 molar, so 0.01 molar, again, we won't worry about sig figs just yet because we're reading this off of the graph. You can see that the initial rate changes. And perhaps it hasn't escaped your notice that what we just did here is we doubled the concentration. And you can see that, in fact, the rate itself has doubled. That is, the initial rate has doubled. And so you can see that in this case, actually changing the concentration does have an effect on the rate. But here's the thing. Changing concentration of a reactant doesn't always affect the rate. Also, changing the concentration of a reactant doesn't always change the rate in a directly proportional way. This is what we're seeing here. We double the concentration, the rate doubles. Sometimes, for certain reactants and certain reactions, you double the concentration and the rate changes by a factor of 4 or by a factor of 9 or some other thing. Or you change the concentration and nothing happens, no change. And that's actually quite informative. It tells us something about the nature of the reaction. So this is the point of this Chem Activity 12, is to find out how does changing the concentration impact the rate? And it can't be predicted by just looking at a balanced equation. You have to do an experiment like what we're seeing here. Okay, and so I'm going to unpack a little bit the details of the experiment, but I just wanted you to look at this graph, see how we read it. Note that I am showing the transition of oxygen gas over the entire time, but really all we're interested in terms of what we're going to do going forward is just this time equal to 0. Next week, when we change our point of view of looking at rates of reaction, we'll actually consider the entire plot. But maybe before we go on, I just want to see if we could extract out one other piece of information from these lines here. As we watch the disappearance of oxygen gas over time, what is happening to the rate of reaction? Oh, okay, so Jacob just says it's going to 0. So in other words, it started, let's say in the upper example, at 2 times 10 to the minus 6 molar per second. And then over time, you say going to 0, so therefore it's say again? Okay, yeah. But to get there, therefore, the rate of the reaction is what? Speeding up or slowing down? Yes. And you see, when you're monitoring the change in concentration of a reactant over time, the most common thing is you'll see that the rate decreases. And again, this kind of points out that the concentration indeed impacts the rate. And one of the things that you could do is actually take tangent slopes all the way along that line to see, oh yeah, indeed, the rate is decreasing. But again, I've commented that we're really going to spend our time today looking at the very beginning of the experiment. Now, I just want to highlight, why do we look at the very beginning of the experiment? It's actually experimentally a lot easier, because when you set up a series of reaction vessels and you're going to add your reactants, you can know what the initial concentrations of your reactants are, because you can take stock solutions for which you've already prepared and you know those concentrations. And then you add them, and then at the point the reaction is just starting, you know those initial concentrations. So that's like what we're saying here, this 0.01 molar and this 0.005 molar. We know those concentrations because that's the concentration of the chemical that we put in there, or after the dilution and making the solution. And then you monitor the rate. So it's just, you have a lot of information available to you. Now, usually we don't present the information in a graph like this. Usually what we do is we present it in a table as such. So just below in your chem activity, you'll see the corresponding table, and you'll see that 3 different experiments are represented. Now, actually, this graph that is at the top of the page, and I've just put to the side here, actually represents 2 experiments. So just to make the connection, you can see that I have here an initial oxygen concentration, and I have a more appropriate number of significant figures. And look, the 0.01000, well, of course, that corresponds to that point right there. And you can see, well, here's the initial rate. Okay, so normally we tabulate this information. Or let us say we have the concentration of the oxygen gas. And of course, that corresponds to that point right there. And here is that initial rate. Now, there are two reactants. And so actually in setting up this experiment, there was some thought into this, that what we're going to do is we're going to halve the oxygen concentration, but because we want to see how does the oxygen impact the rate, look at what we do with the NO concentration between those two experiments. Yes, we keep it constant. So you didn't see that in the graph initially, but that's a strategy so that we can be sure to figure out, well, what's going on with that particular reagent. And then if you look at the third experiment, you can see that what we're doing is we're changing the concentration of the nitrogen monoxide. Okay, and what we can do is, let's say, compare experiments. I'll do it this way, 1 and 3, and you can see there's a change in concentration of the nitrogen monoxide. We have it, but the strategy was to keep the oxygen's concentration constant between those two. And you can see that having that concentration does indeed have an effect on the rate. So both reactants affect the rate. But that's not good enough. That a little analysis is just fairly superficial. Usually we want to go a little deeper. And what we want to do is come up with what we call a rate equation. So you'll see under teaching model number 2, where the table is presented, I offer this key question. I say, use the information in the table above to calculate the rate law and the rate constant. Now, a minute ago, I said rate equation. I should have said rate law. That's what I meant to say. I'd like to show you the format of the rate law. It's always going to look like this. Rate is equal to K, and this is specific for this particular reaction. The concentration of NO2 times the concentration of O2. Okay. K is a constant that we'll be determining. But you might say, okay, we've come up with the rate law. What's the big deal? The thing is, what we don't know are what the exponents are next to these concentration terms. And typically in kinetics, there's no really good reason here, we use the exponents m and n. If you want to use x and y, fine. If you want to use O and P, that's fine. Or A and B, that's fine. I will be using M and N, right? Okay, so really, this whole experiment is designed to figure out, well, try that again. This whole experiment is designed to try to figure out what are those exponents. So there's a longer, more mathematical way, and there's a shorter conceptual way. I'm going to show you the mathematical way first, and then once hopefully you feel relatively comfortable, we'll do the more conceptual way. Personally, I prefer the conceptual way, but it has to be done appropriately. Okay, so here's the idea. What we're trying to do, as I mentioned, is come up with this rate law. So a good place to start is actually to write that out. That's going to serve as, in a sense, as a template for doing your mathematical work. Next, you can see I wrote it out again. And you say, what? What's the point? Because we're going to do some mathematical work. And our first goal will be to compare experiments 1 and 2. And I just put out something else that I didn't quite mean to yet, but I'll explain. So we're going to compare experiments 1 plus 2. And you can see that for experiments 1 plus 2, what's happening is the nitrogen monoxide concentration is kept constant. So I'm just going to kind of remind ourselves about that. So nitrogen monoxide concentration equals a constant. Remember, those square brackets represents concentration of. And the goal of looking at experiments 1 and 2 is to see how does changing the oxygen concentration impact the rate. So I say start off by writing the rate law template, if you will, and then you write it again, and it's like you're dividing one by the other. And what you're going to do is, in order to solve this next part, is you're going to remove any terms that are constant. So I've mentioned that K represents a rate constant. I'll say a whole lot more about rate constants going on, but it's a constant. It's a constant for however way you run the reaction at a particular temperature, and we'll assume temperature is constant. We just said that the nitrogen monoxide concentration is constant. So then my overall equation reduces then down to this simplification. Now, right now, it seems kind of like, what? Like, it doesn't really have any meaning. But it would have some meaning if we now say, okay, in the numerator, that will correspond to one of the experiments, and the denominator to another experiment. It doesn't matter how you assign these things, except there is an easier way. I'm sure some of you are way better at math than I am. But for me, I find it easier if the bigger number's on top in the numerator. And you can always make the decision that the larger value will be in the numerator. Okay, so we'll do this. Rate 1, this would be concentration 1. Rate 1, concentration 1, or rate 1, concentration 1. Oh, what did I just do? Try that again. Rate 2, concentration 2. Rate 2, concentration 2. And as I say, that was fairly arbitrary, but it's just that I know that the rate 1 and the concentration 1 are larger, so that when we do the math, we'll get a number that's larger than 1. And I just find that easier to conceptualize or work with. Next, we fill in the values. So I actually write in the numbers. So I write the initial rate. Now remember, these are rates at time equal to 0, or like as soon as the reaction has started. Now I've included the units, but technically, because we're looking at this ratio, even those rate units will cancel. You'll note that I didn't write in the concentration units. Again, the concentration units will cancel, but you just need to make sure that, of course, the units are the same on the top and the bottom. Again, the goal here is to solve for what that exponent is. So if you're writing all this out and you're not like writing in the exponent, make sure you write in the exponent. That's the key thing here. So now let's simplify. So if you divide 2 times 10 to the minus 6 by 1 times 10 to the minus 6, well, obviously that's 2. Now, you know that in these courses, especially when we're dealing with mathematics, we really want to emphasize significant figures. But here's the thing. These exponents that you're trying to solve for the purpose of our first-year chemistry course, they will either be a 0, a 1, or a 2. Now, in the research world, it's possible to have 1.5. It's possible to have a whole bunch of different exponents. For our purpose, it's either going to be 0, 1, or 2. So worrying about sig figs, at least in lecture, of course, in lab, you should always worry about sig figs. It's not an issue. And the idea here is we're trying to solve for what is n. And so in other words, 2 is equal to 2 to what power, such that that's a valid equation. So for instance, if I stuck in a 0 here, well, 2 to the 0 is equal to 1. So that doesn't work, right? 2 to the 2 is equal to 4. That's not a valid equation. So what must that exponent be? Well, n is equal to 1. That's what we've just found out. Now, you can, of course, for those of you who are more comfortable with math, you can leave this as an n, take the log of both sides, and do a log manipulation to solve for n, and that works perfectly well as well. But in my opinion, Just take a look. Yeah. N has to equal 1 in this case. And so after you've done this little bit of analysis, we're only partway through, we're only halfway through. It's a good idea to kind of summarize what we've just found out. So we would say, well, N is equal to 1. And then we would make the conclusion, therefore, the reaction, and there's a certain kind of terminology here that's quite important. The reaction is first order. And then I'm going to abbreviate here, with respect to the oxygen concentration. N is equal to 1. Another way of saying that, the reaction's first order. Another way of saying this is the relationship between rate and concentration are directly proportional. As we saw, if you double one, the other doubles. That is what we've just found out. You can't find this out by just looking at the balanced equation. Now, some of you might look at the balanced equation right now and say, oh, the coefficient's 1. That means it's first order. No, that's entirely a fluke that it happened to be that coefficient is 1 and the reaction's first order. You have to determine this experimentally. So what we just did here is the first part of the analysis to compare experiments 1 and 2 to find out about the oxygen gas by keeping the nitrogen monoxide constant. Now, perhaps I should have warned you to save some room because we have another experiment or another analysis to do. So hopefully you didn't write too large or you've got somewhere where you can expand out to, because we need to do the next part. What two experiments should we compare? We just did 1 and 2. Yeah, and so Jacob suggests 1 and 3, and I agree with him because it's those experiments where we keep the oxygen concentration constant. Now, you're going to see a little bit later on that once you have found out one of the exponents, it is possible to find out the other exponent even if the concentrations aren't constant because you already have one of the unknowns. But it's still easier if you can, for both reagents that in one case, one of the reagents held constant and the other changes. And then in another set of experiments, the other reagents held constant and the first one changes. So we're going to now compare experiments 1 and 3. So let's do this analysis. So now this is experiments 1 plus 3. I think it's actually a really good idea to do that little title there, just one to remind you. And then if I'm looking at your work, I know what to look for. It's like, oh yeah, they're comparing experiments 1 and 3. And what's significant about experiments 1 and 3 is now the oxygen's concentration is held constant. Again, just to remind you that in the table, I say oxygen naught, which again means the initial concentration, means the concentration before the experiment has started. Okay, remember the procedure. I kind of overrode, but that's okay. The procedure is to write out the rate law template and write it again and put one divided over the other. And again, I would look to put in the numerator the larger term. So in this case, the larger term or terms happens to be experiment 1. And we know that the concentration of oxygen is constant. We know K is constant. So we're more concerned about the nitrogen monoxide one. And then down here, this will be rate 3 and concentration 3. Which therefore leads to the following. Now, maybe you're starting to get the idea that if you already know what you're doing here, you actually really don't need to write this first statement. I mean, we had to at the beginning just so you could see where we were going with. What I've highlighted in red there, you actually don't need to write that. Why not just jump right to this? If you know that you're comparing experiments 1 and 3 and oxygen's concentration is constant and the rate constant is constant, just jump right to that. Okay, so I'm going to pause here for a second and ask you to start there and input the work to see if you can find out what is the exponent m. And remember, it's either going to be 0, 1, or 2. All right, so more officially, I write out the different rates. I can, of course, cross out the units there. They're going to cancel anyways. The concentration units, I didn't bother writing in because they will cancel. My goal is to solve for m. So now I divide, and just be careful with the numbers. Don't forget the exponents, or, just get the context here. 2 times 10 to the minus 6 is actually 4 times larger than 5 times 10 to the minus 7. It's kind of like taking 20 and dividing by 5. And of course, 0.01 divided by 0.005 is equal to 2. So you should get something like that. Again, I like to have the thing that's larger on top. It just makes the math a little easier. And the kind of picture, okay, yeah, what I did here is I doubled the concentration. Therefore, what happened to the rate? By the way, you don't always have to just double the concentration. It's convenient. Tripling the concentration would be fine. Having concentrations, another way of the reverse of doubling. Okay, so the idea is we're trying to figure out what is the exponent m here. And again, you could do it by trial and error, like I did before. So you put a 0 in, 2 to the 0, well, that's equal to 1. 2 to the 1, that's equal to 2. Okay, well, then it's going to be 2 to the 2. So 2 to the 2 will give us 4. That's a valid equation. Therefore, m is equal to 2. And then we make the concluding statement. Therefore, the reaction is, and now we don't say first order, but rather we say second order with respect to, and now because we're trying to find out about the nitrogen monoxide gas, second order with respect to the nitrogen monoxide gas. So again, the instructions were use the information in the above table to calculate the rate law and the rate constant. Well, in order to come up with the rate constant, we actually need to fully write out the rate law. And if you're asked to write the rate law, we really do want you to write out the rate law. So I hope you have a little bit more room still. And the idea is that after having done all of that work, you should then write this out. Like, write it out. It's not enough, really, to just say, the exponent n is equal to 1, the exponent m is equal to 2, or it's first order with respect to oxygen gas, it's second order with respect to nitrogen monoxide gas. If you're asked to write the rate law, write it. And this is the rate law. Okay, this term, this equation is called the rate law. Okay, so write out that whole thing. Note that it essentially shows you how changing the concentration of any of the reactants will impact the rate. It also will allow us to determine the value and the units for the rate constant. Knowing the rate constant for a reaction actually is really useful, and its units as well. So there's some interesting connections. It's going to take some time, though, to unpack why the rate constant is so a value. I will point out that the way that we're writing the rate constant here, so one, it's italicized, but of course, if you're writing in pen or pencil, it's hard to do that. But note that it is lowercase. That's intentional, because you may remember that actually we have a capital K that's used for constants related to equilibrium, concentration of product over the concentration of the reactants. That's a different K. So unfortunately, we have a bunch of different Ks in chemistry. We also have capital K as the unit for Kelvin, right? So small letter K. So solve for K. The math here is not hard. It's just straightforward algebra. So you're going to rearrange to solve for K. But one of the things that you might be wondering is, well, what should you put in there? And the idea is that you have 3 experiments here. It doesn't matter as long as you put a consistent set of data. So I believe what I show you is I'm going to take all the data from experiment 1, but you should come up with the same answer for all the data in experiment number 2 or all the data in experiment number 3. K does depend on temperature, but we're assuming that all of these reactions occurred at the same temperature. Okay, so now I input the values. And here I'm going to write something. I don't know if this is going to register. Actually, maybe I'll do it in a different pen. Make it stand out. Actually, that doesn't look very good, does it? But hopefully you can read that. Units. Maybe I put an exclamation mark. Units. So when we were determining the rate law, the units didn't matter really, because as long as, it was molar and molar per second kind of thing, they canceled out. But the units for the rate constant are actually really informative. So here, there is no shortcut. You got to put in the units. So I put in the units for rate. I put in the units for each of the concentrations. And then I want to come up with a final number with the corresponding units. Note that when we have this square term right here for the concentration of NO, that means the number gets squared, as do the units. That's molar squared. So the final value here will be, well, I'm kind of compressing things first of all. So the top 2 times 10 to the minus 6 molar per second. At the bottom, if you multiply those numbers out, 1 times 10 to the minus 6, and that's molar cubed. And here, yes, you should be paying attention to sig figs. And so what's dictating the sig figs actually is the final rate there. And so in terms of an answer, the numeric answer is 2.0. You can see that one of the molar on the top will cancel with one of the molar on the bottom there. And so we finally end up with 2 seconds to the minus 1 molar squared, which actually might look really bizarre to you. One way of writing this would be this, because remember, seconds to minus 1 means 1 over second. So you could say again. Okay. Well, see Jacob just said, this seems inconsistent, and I agree entirely. So what I was writing here was just the pure solving, right? You could then write it as I've just written it, where you write both of them in the denominator, but the preferred method would be this, and what you'll be seeing going forward, minus 2 seconds to the minus 1. That's typically what we would do. Molar minus 2 seconds to minus 1. So we have completed what we were asked to do, but often you're asked to do one more thing. And so again, hopefully you got a little bit more room. This won't take up a lot of space. You're often asked also to state the overall order. And I'll confess, often in a test, well, I shouldn't say often. Sometimes in a test, students will get this wrong. And it's a little discouraging, because the overall order is simply M plus N. It's just add up all the orders. And you'll see in a minute, there's a reason why we do this. So what would be the overall order in this case? Yeah. Right. So, what we did here, and I just want to remember, I think M is 2 and N is 1. I couldn't remember which was which, but 2 plus 1 is equal to 3. Here's why we make that connection. Any reaction that has an overall order of 3 will have these units. I mean, the math just plays it out like that. It has to be. But what this means is, if you know the units, you know the overall order. If you know the overall order, you know the units. They are interchangeable. And you'll see that there's only so many possible permutations. Really, most reactions don't go beyond overall order 3. Often we'll have overall order 1 or 2 or 3. And so connected to that are a set of units. And so I'll show you some charts later on, but that molar to the -1, second to the -1, that's very consistent with overall order 3.